Okay, hello there. In this video, I'm going to talk about the binomial theorem. And this is already the last part, the last section, shall we say, of our Module 1 in our number theory major subject. This is still, again, in the fundamental properties and preliminary considerations. So the binomials we know are sums of two terms, right? Sums are difference of two terms, and they occur often in mathematics. This whole section, the last section we are going to have, is going to show us to expand positive integral powers of binomials in a systematic manner. So the coefficients and binomial expansions have several, well, interesting properties, and we'll begin our discussion with what we call the binomial coefficients. Okay, binomial coefficients. Okay, so maybe this lesson or these coefficients you have already saw them when you have your first course in probability or statistics. So we're going to let n and r to be non-negative integers. So meaning they are whole numbers in our definition. So the binomial coefficient, we write this as n r. Okay. Some books also denote them as C and R, or you can see this in your calculators, NCR. Okay, in basic mathematics, we always use this NCR, but here in our book, we're going to follow this denotion. Okay, so this is defined as um, N, N taken R, N choose R rather, is equal to N factorial all over R factorial times, sorry, times N minus R quantity factorial. Okay, so this is if R is less than or equal to N. Um, it is 0 otherwise. Okay. Oops. Okay. So the term binomial coefficient was first coined or introduced by the German algebraist, okay, Michael Stiefel, um, born on 1486 to 1567. So in his best known work, Arithmetica Integra in 1544, Stiefel gives the binomial coefficients for n which is less than or equal to 17. Okay, so to give you one example of this binomial coefficients, say we have, as an example, 5 choose 3. Anyways, we read this as 5 choose 3 and choose r and choose r. Okay, 5 choose 3. This is going to be equal to 5 factorial all over 3 factorial times the quantity of 5 minus 3 factorial. This is clearly equal to 5 factorial all over 3 factorial times 2 factorial. And then expanding, so we have 5 times 4 times 3 times 2 times 1, and then 3 times 2 times 1 times 2 times 1. Okay, and then we can do some cancellation here in this part of our solution. For example, we can cancel this 3, 2, 1. This factor is 3, 2, 1. And we can also factor the 2. We can cancel this 2 here by this 4. If we're going to do that, this will become 2. Okay, and then clearly the answer here is 5 times 2 divided by 1. It's going to be 10. Okay, so that's how we use our binomial coefficients. Again, this is like the um, combinations, okay, in our probability, in our basic probability, alongside with the permutations, if you can remember. But here we're going to call them the binomial coefficients. Okay, so the answer here is 10. So to add up here, by definition, we have n taken 0 is equal to 1 is equal to n taken n at a time, which is equal to 1. Okay, so this is the part where we end with our binomial coefficients, but we're going to use that concept in the next theorem that will be shown. Okay, so the following theorem shows an important recurrence relation satisfying or satisfied by the binomial coefficients. It is called the Pascal's identity, of course, by the great mathematician and philosopher Blaise Pascal. So let's state this formally. Theorem. So we call this Pascal's identity. Okay, so what does it say? So we will let n and r to be part of the natural numbers or positive integers, where um, r is less than r is less than or equal to n. Then we can say that n choose r is just equal to n minus 1 choose r minus 1 plus n minus 1 choose r. Okay, so that's the Pascal's theorem. So we're going to give a proof for that. So let's have a proof. Maybe we can move this to the next page so that it can fit. Okay, so let me write it again. I'm sorry. So theorem, Pascal's identity. So again, let me write this. So let n and r be positive integers, where r is greater than or equal to less than or equal to n. Then n choose r is equal to n minus 1 choose r minus 1 plus n minus 1 choose r. Okay, so let's give a proof for this theorem here, Pascal's identity proof. So what we're going to do is we will equate the left hand side and the right hand side so to show that they are equal. So why don't we just just simplify this right hand side here and make it equal to the left hand side? That will be better than expounding this left hand side here. So we will simplify. Let's put here, we will simplify. We will simplify the right hand side. Let's abbreviate that. Um, that is, uh, it is equal to the left hand side. Let's abbreviate it also. Okay, so to show this, let's have this. Just going to take this, and then in the end, we're going to show that it is equal to n choose r. Okay, so let's have that. We have n minus 1 choose r minus 1 plus n minus 1 choose r. It's equal to, so let's expound this using our binomial coefficients. So what we have here in before is that binomial coefficients are equal to n factorial, the first term, all over the r factorial, the term before, the term below, and then n minus r, that is the term above minus a term below. So let's follow that pattern. Okay, so for here, oops, term above, and then put a factorial, n minus 1 positive factorial. Factorial, and then we're going to write the item below, r minus 1 factorial, and then we're going to write the 1 above minus the 1 below. So we have n minus 1 minus r minus 1 positive factorial. Let's simplify that better later. And then for the second term, we have n minus 1 positive factorial. Okay, and then r factorial, that's the term below. And then we have n minus 1 minus r positive factorial. So this needs fixing. Okay, let's try to substitute or simplify it first. You have n minus quantity n minus 1 factorial. So we have r minus 1 factorial. And then in this part, we can see that distributing the minus sign here, it will give us negative r. Likewise, it will give us positive 1. So negative 1 plus 1 is going to be 0. So what we have here is n minus r, which is left. I hope you saw that. So my negative 1 plus 1 is 0. Okay, plus n minus 1, okay, factorial is equal to r all over r factorial. Maybe it's better to arrange this correctly, since r is greater than or equal to rather n is greater than or equal to r, so we can rearrange it in such a way that it will be like this. Okay, so that n is the biggest one minus the second to the biggest second term, and then minus 1 constant. Okay, so next up is that we're going to introduce or find the LCD of these two terms. And if we do that, we need an additional r in this first term, and we need one n minus r in this second term. So if we'll do that, what we'll have is, so that'll be r. That this is our additional r. Okay, then copy the rest. N minus 1 factorial times r minus 1, we're just going to copy now what is certain above, times n minus r 20 factorial. Plus, in this part, we are lacking one n minus r, so we'll put here n minus r times n minus 1 factorial all over r factorial times n minus r times n minus r minus 1 factorial. Okay, so I think we cannot fit it there. Let's move to the next page. So remember in here, okay, what are we going to think here? So notice that r minus 1 factorial is all the parts after r minus 1 is r minus 2, r minus 3, r minus 4, and so on. So why don't we just merge it into r times r minus 1 times r minus 2 times r minus 3. So therefore giving us an r factorial in this part of our equation. So writing that down in the next page, what we have is r times n minus 1 factorial all over r factorial, right? So that became, oops, this one became the r factorial. Oops. Okay, this one here. So this one became the r factorial. Likewise here, notice that this one, okay, can also be merged, okay, because we have n minus r minus 1 factorial. The next terms there are n minus r minus 2, n minus r minus 3, and so on. So if we're going to add up n minus r in the first part, so we haven't decreased by 1 yet. So this becomes n minus r times n minus r minus 1 times n minus r minus 2. So we're just going to stick it here so that n minus r can be made as a factorial notation. So let's put it here. Oops. Oops. N minus r factorial plus I think I forgot. N minus r times n minus 1 factorial, n minus r times n minus 1 factorial, all over, what was that again? R factorial, okay, r factorial times n minus r factorial. So in this part, we can see that the denominators are the same. So I think we can combine them now put them above one denominator. So we have n minus r 22 factorial. And then we can see here that we can, just put it as it is. R times n minus 1 factorial plus n minus r, times n minus 1 factorial. So from here, we can see that there is a common factor in both terms. That is the n minus 1 factorial, and we also have an minus 1 factorial here. So if we're going to get those terms, we are doing factoring by grouping. Let me write the denominator first. Factorial. So let's write that outside. So we have n minus 1 factorial. Okay, whatever is left here is, in this part, first part of the term is r. Okay, let's use the brackets, r. And then plus, notice what is left here is this one. So n minus r. Okay, and then next up here is that maybe we can just simplify what is inside this groupings. So n minus 1 factorial. So we have r plus n minus r. So r minus r is simply going to give us n. Okay, since r is cancelled. R is cancelled. Um, let's make a let's use a different color. So r is cancelled here. R is also cancelled here. So therefore, what is left is just n. Copy the denominator. R factorial times n minus r quantity factorial. So again, by the same concept that we did in the slide before, like over here, okay, so for example, just to give an example, so we have r minus 1 quantity factorial, we put up the r beside it, so therefore we have an r factorial. So in the same manner, this is just what we're going to do here. We're going to put the n in this part, okay, so that we can get an n factorial. Okay, again, so that we can get an n factorial. So if we'll do that, this will become n factorial all over r factorial times n minus r quantity factorial. And yeah, wait a minute. This is already the n choose r, right? So this is, by definition, this is the n choose r. Let's go back to our slides before. Okay, here it is. Here. If you can remember, this is our n choose r. This is our formula. N choose r equals n factorial all over r factorial times the quantity of n minus r factorial. So we ended up in that answer, which is n minus r factorial. Therefore, we can say that the right-hand side, this one here, the right-hand side, is equal to the right-hand side, okay, is equal to the left-hand side. Okay, again, we have proven that this right-hand side here is equal to your left-hand side. So therefore, the Pascal's identity is is indeed correct. So this is the end of proof already. Okay, this is n. Okay, there. Okay, so that's the Pascal's identity. Okay, and what is the use of this Pascal's identity? Actually, I have a paper about this, proving using Vedic mathematics. Maybe I'll show you that in the future. Okay, so the various binomial coefficients. Okay, we're going to start now in the Pascal's triangle. Okay, this is the culminating part of our today's video. So the binomial coefficients n choose r, where r is less than or equal to n, which is greater than or equal to 0, can be arranged in the form of a triangle. Okay, this triangle is what we call Pascal's triangle, which has a lot of amazing properties. Okay, so let me show you that. Okay, Just take note, although Pascal's triangle is named after Pascal, Blaise Pascal, it first appeared in 1303 in China. Okay, this Chinese mathematician Shu Kie, sorry, I don't know how to pronounce. Okay, already saw this Pascal's triangle. So what we're gonna do, again, we have n and r, n choose r. We say by the Pascal's identity that it is equal to n minus 1 choose r minus 1 plus um, n minus 1 choose r. Okay, so we're going to make use of this what do you call that, of this identity. This is the Pascal's identity. So what we're going to do is we're going to start with shall we start with 0 0, let n equals r equals 0. Okay, so what we're going to do is to have this first part to be 0 0. Okay, what are we going to do then? So since this is 0 0, we have nothing to add up. So notice that in the first terms here is n minus 1, n minus 1. How about if we're going to add 1 there? So that will give us the n, right? If this is your n minus 1, if that's your point of view, this will become 1, this will become 1. And in the second term below, we saw that this one is r, this one is r minus 1. Okay? So r minus 1. So if this is r minus 1, we're going to put 0 here. And if this is r, so therefore we're going to put 1 here. Okay? Now, we're going to continue in this manner. So again, this is n minus r. We're going to put an r, which is, we need to add 1 there, need to add 1 there, we need to add 1 there. And then, since there are 3 terms, I think we can put 0, 1, and 2. 0, 1, and 2. And then, by the same manner, we have 3, 3, 0, 3 choose 1, 3 choose 2, 3 choose 3. Okay, and then the last for this example, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay, so let's try to substitute the values of this Pythagorean theorem over here. Okay, so let's have this. So what's the value for 0 choose 0? So if you want to substitute that, that's 0 factorial all over 0 factorial times 0 minus 0 factorial. Okay, so that will be equal to 0 factorial is 1. So 0 factorial is 1. So that's 1 over 1. That will give us the value of 1. Okay, how about let's fit it here? Let's put it here, 1. Okay, what's 1 choose 0? Okay, 1 choose 0. So again, let's use our calculators, or I mean, let's solve for it. You can use your calculators, of course. So we have 1 factorial over 0 factorial, and then 1 minus 0 factorial. Pretty much it's still 1. Okay, 1 factorial is 1, 0 factorial is 1. So therefore, we have 1 over 1. That's going to be 1. Okay, how about 1 over 1 factorial? I think that's the same thing with 0 over 0. So 1 minus 1, 1 minus 1 is 0. So that's still 1. How about 2 choose 0? So 2 factorial, um, we have 0 factorial times 2 minus 0 factorial. That's going to give us 2 all over 1. 0 factorial is 1. 1 times 2, rather, that this is 2, rather. So this will give us still 1. So this is 1 here. Okay, how about 2 choose, how about 2 choose 1? So we have 2 factorial all over 1 factorial times 2 minus 1 factorial. Okay, so this becomes 1 factorial, 2 over 1. So this is going to give us 2. Okay, and lastly, 2 choose 1, 2 choose 2 rather, is still 1. Okay, 3 choose 0, that's going to give us 1. Okay, 3 choose 1, so 3 factorial all over 1 factorial times 3 minus 1, 20 factorial. So we have this is going to become 6. This is going to become 2. 2 times 1 is 2, so that's going to give us 3. Okay, that's 3. Similarly, we have 3 factorial for this part now, for this part. So we have 3 factorial all over 2 factorial times 3 minus 2 factorial. And pretty much, I think we're still going to end up with 3 factorial is 6. This is 2 factorial times 1, so that's just 2. So this is going to give us 3. 3, and this is going to give us 1. Now, by the power of the Pascal's identity, I think we don't need to really solve everything from here. So notice here, we can say, for example, we can imagine this number. Imagine this as n choose r. So if we're going to add these two numbers before it, 1, 1 choose 0, and 1 choose 1, this is actually your this number. Okay, and this actually is your number here, right? So meaning this number, okay, has its two addends right above it. Okay, so we have n choose r, our n is 2, for example. Our n is 2, for example. Our r is 1. So what is n minus 1? That's 1. What's r minus 1? 0. So 1, 0. 1, choose 0. That's it. N minus 1 is 1. R is 1. So 1, choose 1. So therefore, by the Pascal's identity, and since we can choose any arbitrary n, choose r here, we can make use of this. So meaning this number here is this plus this. And this number here, okay, is this plus this. Okay, this number here is this plus this, and then so on and so forth. Okay, so therefore, I think from here, we can finish this without even answering everything in this Pascal's triangle. So this is, imagine there's a 0 here, so that's going to be 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then 1 plus 0, there's a 0 in this part. So there. Then continue, we have 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and so on. And then I think we can continue this infinitely or finitely if you, ideally finitely, but again, we can do this all day. Okay, we can do this all day. So this becomes 21 and so on. It doesn't fit anymore. So this particular triangle here that you're seeing, though it's not really a perfect triangle given the area in the screen that I can fit it, okay, this is called our Pascal's triangle. Okay, and Pascal's triangle is the one that we're going to use when we tackle the binomial theorem. Okay, so that it will be easier for us to answer problems involving the binomial theorem. Okay, and also it has some very magnificent and awesome properties. I think I will create one video separate for that, specifically for Pascal's triangle, so that you can see its magnificence. Okay, so for now we will end here. Thanks for watching, and don't forget to subscribe and like. I'll be creating the binomial theorem in the next video, and maybe that will be the our last video for the number theory module 1, fundamental properties and preliminary considerations. So thank you very much for watching, and see you guys soon. Bye.